Hello, students. Talking about section 2.2. Going to hit a few of the big pictures. Just remember, in bold, there's definitions. So this is what we talked about. Set is a collection of objects. Individual objects are called elements of the set. Set uses the little squiggly brackets, and we also use this symbol right here to represent an element. And let me get my little pointer so we can kind of see where I'm looking at. There we go. So this element right here, this little symbol is the element of. So if you have a set defined as capital A and it has 3 elements in it, you could write B, lowercase b, is an element of A. So again, what we're doing is we're creating a statement. So B is an element of A is a statement, and it's either true or false. Now, if it's false, we could change the symbol to be the not an element of symbol. Okay. But again, you're just looking at what is included in the set. So if the set does include an A, a B, and a C lowercase, then the number 3 is not an element of A. Right? Just like with statements, a set has to be well defined. So if we say we're talking about the set of all tall people, that's not well defined because what is tall to one person may not be tall to another. So instead, we might want to change that to say, oh, it's the set of all people who are over 6 feet tall. Okay, now that is well defined. So who's in the set? You to ask a person, how tall are you? They say 6'2". That person is in that set. Someone else says, oh, I'm 5'8". Oh, you're not in that set. Okay. So we have a couple different ways to do it. We list elements, or we do a set builder. And again, the way the textbook defines that is the such that. I described in class a way of thinking about that using the words as long as. So the set is equal to all elements called X as long as X is a natural number and X is less than 5. So that group of numbers that is being referred to here, you could write that set of numbers out as just 1, 2, 3, 4. In this case, I think probably most of you would prefer the first method, just write the numbers out. But if we're talking about an infinite set that would go on forever, and we wanted all the natural numbers bigger than 5, maybe this second approach helps to define very clearly what is in the set and what is not. Okay, so that's the idea for those pieces. All right, let's take a look. We'll keep going. Wait, I gotta turn the page. Digitally turn the page. Let's see here. Yep. So set builder notation, you could have a description. Notice this one would be very, very hard to list out. The set of all numbers X, as long as X is a decimal between 0 and 1. Try to list all of those out, and we've got a real problem. 0.8, 0.9. Yes, those are all true and in the set. But what about 0.81, 0.82, 0.83, right? All of those. What about 0.811, 812, 813? All of those decimal numbers would be in there. So listing them would be problematic. And that is why the description has to be very clear. So there's an example in the textbook that says, hey, why don't you try writing some set builder? And even numbers, they're all multiples of 2. So you could just say, oh, multiples of 2. That's 2 times n, as long as n is a natural number. If you want odd numbers, well, odd numbers are always 1 less than an even number. So we could write that as 2n minus 1, as long as n is a natural number. Now, what you could also see is there's a connection here with everything we've done with sequences. So when you had a sequence 2, 4, 6, 8, 10, right, you could have said, okay, well, I'm going to write this as a general term. And the general term that you might write, an, would look like 2 times n. Okay, how would we get that? Well, you would write your first term. This goes back to chapter 1. You write your first term plus my common difference times n minus 1. This is what we did in chapter 1. Distribute using a little bit of algebra, and you've got this beautiful connection here where the minus 2 and the plus 2 go away, and you're left with 2n. So don't think this is a new skill. This is not a new skill. We're just kind of repackaging it. So if you had a sequence that was 1, 4, 7, 10, you could say, ooh, wait a minute. Every term in that sequence would look like 1 plus 3 times n minus 1. and then distribute. 1 plus 3n minus 3, and then combine your like terms. So you get 3n here, and a minus 3 plus 1 becomes a minus 2. So every term looks like this. Well, if you want a set of all those terms, then you take your 3n minus 2 and you just say, I want all of my terms to look like that. Okay, so don't think this is different. This is not, just an extension of what we did in chapter 1, and that's why we did chapter 1 first. Okay. Again, if you get a sequence listed and they tell you what kind of numbers you're looking at, you can just plug the numbers in to check it. Sometimes it's more of a description, an even natural number less than 8. Well, it has to be a natural number, and it has to be less than 8. So where do those intersect? Okay. Then we get the definition of equal. Two sets are equal. We put an equal sign between them. If they're not equal, we put a slash between it. But the definition says two sets are equal if and only if they contain exactly the same elements. Here's our if and only if. This is biconditional. So if they contain the same elements, then we call them equal. If we call them equal and we put an equal sign between them, then they contain exactly the same elements. So it's biconditional. Let's turn the page. All right. One-to-one correspondence. Again, we talked about this in class, but this is the idea of pairing things up. Okay. So if you can pair them up, not necessarily and necessarily have to be ordered pairs like we've done before, but we can actually write out all of the one-to-one correspondences. We can list them all out. If we want to put it in table form, we could write them out if we wanted to. But matching each person with one of the lanes in a swimming competition is a way of kind of making a one-to-one correspondence. Now, in class, we talked about taking this and saying, well, how many people are in this first set for Thomas? Thomas is, if we chose Thomas first, Thomas would have 3 options to choose from. So there would be 3 total options for Thomas. Then we come down here and here's Dick. How many options does Dick have? Well, let's say, I don't know what Thomas went. Let's just say Thomas had to go to something. That would leave 2 remaining options for the next person. And then Mary, how many did Mary have? Well, by the time the T and the D have both chosen, Mary only has 1 left. So there's only 1. And what we can see is if we wanted to count the number, that we would end up with 6, and we can see that there were exactly 6 if we wanted to match them all up. So it's a good connection between some of the skills that we've already had. I'm going to jump forward another page because these are moving fairly quick. So one-to-one correspondence. If the elements can be paired so that for each element of the first set, there is exactly 1 element of the second, and for each element of the second, there's exactly 1 element of the first, then we call this a one-to-one correspondence. So if you had 4 swimmers and 4 lanes, yes, this would be a one-to-one correspondence. How many correspondences are there? Well, there would be 4 options for A, 3 options for B, 2 for C, and 1 for D. So 4 times 3 times 2 times 1, which would give you 24. Now you could also visualize it here. This is another way to do it, visualizing, but any which way you want, especially if you're just trying to count them up. We don't have to necessarily draw pictures for every single one of them. But this brings us to an interesting counting principle. If we're trying to count something up, it may be quicker to use a bigger principle instead of trying to draw them out for each situation, and that is known as the fundamental counting principle. If an event can happen in m ways, after it occurs, the next event can occur in n ways, then the event m followed by n can occur in m times n. I know that looks a little bit vague, but think about it. Give M a title. Okay. Event M, choosing a swimmer, and event N, choosing a lane. So how many ways can I choose a swimmer? 4. How many ways can I choose a lane? After it has occurred, I selected the swimmer and I paired them up with a lane. How many ways can I select the next person? So the next person would be 3. So 4 times 3. And then if I want to go to the next person as well, 4 times 3 times 2. Okay. All right. Let's see here. So equivalent sets. Ooh, slightly different than equal sets though, right? So equivalent sets is linked with a one-to-one correspondence. So the lanes, there were 4 lanes and 4 swimmers. We said there's a 1-to-1 correspondence. You can kind of see them pairing up with my fingertips. Boom, 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 boom. If they have the same number of elements, we can make a 1-to-1 correspondence. But saying these 2 sets can make a 1-to-1 correspondence is a pretty big mouthful. So we kind of shorten that down and we call those sets equivalent. And the equivalent sets have a little kind of squiggle symbol that we put between them. Do not mix them with equal. If 2 sets are equal, they will be equivalent. But if they are equivalent, it does not mean that they must be equal. Okay. So be careful. Take a look, compare it. And it says here, even a good example here, if you're kind of using the book, compare the sets using the terms equal and equivalent. So you can look and see that B and C, these 2 sets, have the same number of elements. So I would say those 2 sets are equivalent because they have the same number of elements. Now look at the actual elements themselves. They're not the same. So I would say B is equivalent to C, but is not equal to C. And that would be different, like for set D and B. Was that like a baby and a dog or something, just so we can kind of be clear? D and B, they have the same number of elements. Boom, equivalent. They have exactly the same elements. Boom, equal. Okay. So that's kind of how we can think about that definition. And this is the last piece, but again, it sounds funky. The idea of cardinality, this term called cardinal, is actually a way of counting. So a cardinal number is how many things are you counting? So if you're counting objects in a set, the cardinal number, so again, they give you an example here. S is the set A comma B. The cardinal number is 2. Okay. So there you go. So again, they give you a nice little link here to our definition for equivalent, because if 2 sets are equivalent, let's pause. Equivalent means they have the same number of elements, meaning we can make a 1-to-1 correspondence. Aha, if they are equivalent, then the number of elements in A has to equal the number of elements in B. Now take a look. This is something that is known as function notation. Cardinal number is a mathematical function. You put something in, so I have this function with parentheses. I put something in, that thing has to be a set, and I get something out, and that thing that I get out is the cardinal number. Okay. So if you have a set, and your set happens to include a 1, a 5, a 9, a lowercase b, and a triangle, right? Then if someone said, well, what is the number of S? You would say 5. Okay. But if someone said, what is the n of the number 1? You would say no, because the thing that I take in has to be a set, not a number. Okay. So you don't take a number in here and get a number out. You take a set and it tells you how many things are in the set. So you could call this error and say, I cannot determine that because this is not a set. All right, and our favorite set. Our favorite set is a set that doesn't have anything in it because it's the quickest and easiest to write. So if you started a set bracket and you ended the set bracket and you said, let me put everything in the middle of all the movies, I don't know who, pick somebody, Quentin Tarantino, all the Quentin Tarantino movies that I like, and somebody says, I don't like any of his movies, then that set would be empty. Okay. Don't put anything in the middle. And then you could say, oh, okay, well, that set, if that was A, the number of things in A is 0. There's nothing in it. Okay. There's also a shorthand. This is I mentioned this in class. The empty set is oftentimes referred to as looks like a 0 with a line through it. So again, be very, very careful here. Do not put a line through your zeros. If you were doing it, I need you to stop because I'm going to say that's an empty set and not a 0. Okay. All right. And they are very clear on this too as well. Like the set containing 0 is not an empty set. And hopefully that makes sense to you. One way that sometimes I'll teach sets is you can think about like a paper bag. Like you go to the grocery store and you can bag your groceries with a paper bag. When you look inside the paper bag, you can see the elements inside the paper bag. So it's possible to have inside your bag like a refrigerator magnet, like with the number 7 on it. Okay, well, that would represent the set that has a 7 in it. Okay, so think about the edges here kind of being the little squiggle symbols there. Okay, but if you didn't have anything in it, then you wouldn't have a 7 and you would have an empty set. This is where things for some students get a little weird because they're like, well, wait a minute, what if I put the empty set into something? So picture this, right? The paper bag. What if I picked a larger paper bag and I put an empty paper bag, that's the red one, into this larger blue paper bag? Is the blue bag empty? And remember, it's kind of like a set. And you'd ask yourself, well, is there anything inside of the blue bag? And you'd look and say, oh, yes, there is something inside. It's an empty paper bag. So you could say, aha, I actually do have something in there. And because I have some object inside, this blue bag is not empty. Something is inside of it. Okay. All right. So that's kind of the fun there. They do talk about finite and infinite sets. Finite set if the cardinal number is 0 or a natural number. They could have just said if it's a whole number, same thing. And so if you have a set that is not, like the cardinal number is not a natural number, that typically means you keep counting and counting and counting and counting and you never stop. We call that an infinite set. So the whole numbers as listed here, is an infinite set. The natural numbers are actually an infinite set because they go on forever. As soon as you count for a long time and then you stop, we would call that a finite set. All right. More about sets. They talk a little bit about a couple pieces here. Not a ton, but just a few basic pieces. The universal set, we talked about that in class. That's for a problem. It's everything to consider for that problem. And when we put a bar on the top of something, like this was the set D, this was what the dogs living in California. I think if you look at the example, so dogs living in California. Well, what would be outside of that? Well, that would be anything that is not a dog living in California. And my universe here is an animal living in California. So if X is a dog living in California, then D complement would be any animal that's not a dog living in California. Okay. So take a look at the definition. Again, definitions are important as we move forward. The definition of complement, written with the bar over the top, is the set of all elements in a given universal set that are not in A. If you prefer set builder notation, you could write a complement as the set of X's as long as X is in the universe and X is not an element of A. So for these questions, we do have to have a universe. We will not be answering questions about complements unless we have a universe to compare things to. Okay. And just for fun, you should be able to see if I take the universe, what's the complement of the universe? Well, that's everything that's not in the universe. Remember, for these problems, the only thing to think about is what's in the universe. So the universe complement would be the empty set. And the empty set complement, what is not in the empty set, you'd be like, everything. So that would be the universe as well. Okay. Last piece here, I think, is subset relationship. A subset relationship is an if-then statement. So all the elements of B are contained in A. That means it's a subset. And you can check the B here. It has a 2, 4, 6. Make sure, does this set over here have a 2, a 4, and a 6? It does. B is a subset of A. But A is not a subset of B because A has a number 1 in it and B does not. So that's what we're checking when we look for subsets. Okay. Definition of a subset. written B is a subset of A if and only if. So notice this is biconditional once again. Every element of B is an element of A. And you could actually rewrite the phrase. Yeah, I like to write it this way. Every element, because every is a quantifier. So that means if X is an element of B, then X is an element of A. I think this helps, hopefully, with what I did in class to remind you that if I want to prove that something is not a subset, I need to meet the condition and fail the conclusion. I need to find an element that's in B, but it's actually not in A. Okay. So there we go. Single element works. That's all it takes. One counter example. Right? So the empty set is a subset of every set. And the reason is because you can never prove it. So if you go back to that definition, right? So if I'm sitting here and I'm saying, okay, I want set A to be the empty set and set B to be anything. It really could be anything. 1, 5, 9, 11. Okay. And somebody says, oh, I think A is a subset of B. Okay. Now remember, in order to prove this false, then I need to find an element of A that is not in B, because this is the definition. So let's see here. We start off by saying, okay, I need to find something that is in A, and I need it not to be in B. That's what I need. So go up to A, and now find anything. Find anything in this set. You're not going to, because it's the empty set, right? It's totally empty. So if it's empty, then the first portion can never be true. And if the first portion is false, then the entire statement is true, meaning the empty set is a subset of every set. There is no way to disprove it. They throw in the definition of a proper subset. Proper subset just means that you can't be equal. Okay. So for any sets, one is a subset of the other. We have A is a subset of B, B is a subset of A is equal to B. We have ways of kind of comparing them. Now, none of those can be true. Some of those can be true. But if A is a subset of B, then at least we should check to see, wait, are they actually equal? Because if every element of A is an element of B, maybe every element of B is an element of A, and that would mean that we have two equal sets. So proper subset means B has to be a subset of A, and B cannot equal A. Okay, so there has to be at least one element that's in one set that's not in the other. Okay. Has to be a subset, but there has to be one extra element. Here's a school book page and a few examples here. They talk about subset relationships. Again, that's a example piece, and they work through a solution there for you, so I'm not going to go through that. And let's see. Oh, yeah, the definition of less than seemed a little bit strange, but if you are pairing things up in a one-to-one correspondence and they don't pair up all the way, then one set has more than another. So if that's true, if it has fewer elements, if A is equivalent to a proper subset of B. So it doesn't mean it is a proper subset itself. It just means it's equivalent to. It has the same number of elements as. So that means you can find a one-to-one correspondence with something that is not your whole set. And if you can do that, one set clearly has more elements. Okay. All right. I think that's, yep, I think I'm probably going to leave it at that. So again, oh, less than, we do write the symbol. Some people remember the alligator. The alligator likes to eat the bigger number. So that's the idea. So I think if A and B are finite sets, what does it mean? It means one number is less than a number. This was one of the homework questions, I think, that the number of A is less than the number of B if and only if A, let's see here, A is equivalent to some set C and C is a proper subset. I shouldn't choose C. You notice that? I'm going to get the symbols all screwy. Let's say here, A is, I'll say K, okay? And K is a proper subset of B. So this is what you need to have happen. So if you want to prove something, like you want to prove that 2 is less than 3, which I know seems a little weird. You're like, are you kidding me? I know it's less than 3. Well, you probably know it's less than 3 because you know it's less than 3, which is a horrible argument. So we need to have a reason why. So what we could do is we could say, okay, well, I'll make set A equal to the number 3, 4, right? Those numbers. And I'll make B equal to 3, 4, 5, right? Okay, so then the cardinal number of B, right? The cardinal number of B is 3. The cardinal number of A, ooh, lost my pen for a second, is 2. And A is a proper subset of B, right? So it's equivalent to a proper subset of B because it's equivalent to itself. So A is a subset of B and it's proper. That means that the number in A is less than the number in B. So the number of A is less than the number in B. And since the number in A was 2, the number in B was 3, we now can say, aha, 2 is less than 3. So everything we do in a math class should have a reason behind it. So we don't just want to say, this is what it is because this is what it is. We want to try to avoid that. Okay. They do talk about the number of subsets of a finite set. Their approach, I guess I disagree with. The reason is they're saying from this information, we make a table and search for a pattern. I don't like that approach because they've already told us if you look for a pattern, it may not continue. So probably not the best idea here unless there's a way to justify it. What I showed in class, I think is probably the better approach, which is to demonstrate how you make the subsets and showing that connection. To me, I think that's a better approach. I don't want to stop sharing. I'm just going to share a whiteboard here for a moment because I think we're at the last. I think that is it. Yeah, and then we get to the assessment. Okay. All right, so let's take a look. Let me jump in here and kind of explain this again if needed. Okay. Whiteboard. Oh, there we go. Okay. All right. So here's the idea. We're going to start small and work our way up. So we're going to start with the empty set. Okay. And I need subsets of the empty set. Now, if you remember anything from what I've talked about so far, remember the empty set's a subset of every set. So the subset for this one would just be itself, the empty set. Okay. So you could write it either way. I'd take either one of these. Okay. So here, what we could say is number of elements and then the number of subsets. Okay, so the number of elements was 0 and it had 1 subset, right? That's basically saying the empty set is a subset of itself. Okay, now let's go up to the first set with something in it. Okay? So I want you to notice then that the empty set is still a subset of this one, right? So I get the empty set. But what else do I get? I get the set itself. So I have 2 now. So one element gives me 2 subsets. Okay. Out of these, only one of them is proper. The empty set is a proper subset. The set itself is not proper because it's equal. Let's continue on and see if we can't make a little bit of a pattern here. So A with B. So this is what I was trying to get to in class, and I hope it clicked a little bit. Because A was already an element here, all of the subsets still exist. So what I get is I get the empty set and the set containing A. I get those for free. Now think about B, and what I said in class was take B and come back over here and put it into each one of these sets. And what you end up creating is a set with B in it and a set with A and B in it. And that gives you all of the subsets. And that's the same thing we did before. If you think about it, this subset came along for free and then put A into it and you get your second one. Okay. Then these two come along for free, and then we take element B and we plug it in, and we get two new ones. So basically, whatever number of subsets you had previously has to continue. So notice I get two that I had before plus two new ones because I put my new element in each one, and that is why I have 4. So lastly, I'll do one more here, A with a B with a C. So all of these, everything here is guaranteed to still be a subset. So the empty set, I'll write it this way, a set with A, a set with B, and a set with A and B. Right? Okay. Now, think about your new element. Your new element is C. Take it and put it into each one of the original subsets because that will make new subsets. When you plug it into the empty set, it now becomes not empty because you put something in it, and you get a C. Put C into the two called singletons here, and I will get an A with a C, and I will get a B with a C. And then don't forget to plug it in for the last one with an A, a B, and a C. So I get this beautiful pattern here that everything I had before still counts. And then I get exactly that same quantity again by just plugging the new thing in. So whatever I had before, which was 4, has to double. And this, as we can see, will continue. So it's not the pattern that makes it true. It's the process I'm using that's going to guarantee this pattern. So the number of elements could be n, and the number of subsets would be 2 to the n. Guaranteed. I mentioned in class there's a lot of other cool things you could do with this. Some of you might remember a beautiful pattern. Let's see, if we start with, there's 1 here. There's one of these, right? And then I keep that 1. That one is right there. And then I put an A in it. So I get one of those, 1 and 1. Then I keep the empty set on the outside. There's one of those. But when I take what I had before, which was one of these, and then I put the new element in, I get a total of 2 because there's 2 of these single sets. And then over here, I still have 1 set, which is everything. Oops. Okay. No, I don't know what that is. Go away. Sorry about that. Something popped up on my screen, said my computer's going to shut down. Hopefully that doesn't happen. Okay, then over here, let's take a look. So I have the empty set again, 1 empty set. I have 1 set that's everything. Then I have 3 singletons, which come from 1 new one and 2 old ones, 3. I have 3 duplicates, which come from 2 of the new and 1 of the old. And I get this beautiful pattern. And this pattern is known as Pascal's triangle. So you could continue, and if you add them up, this is what's kind of cool. If you add them up, you get this beautiful pattern. 1. 1 plus 1 is 2. 1 plus 2 plus 1 is 4. 1 plus 3 plus 3 plus 1 is 8. 10, 14, 16. I get this beautiful pattern where the total number is always double, but I actually can see how many of each type of subset I would have when I look at this. So if I was looking at this and saying, hey, how many in a set with 3 elements? Okay, so I come down to this line with 3 elements. I will have 1 set with no elements, 3 with 1 element, 3 with 2 elements, and 1 with 3 elements. Boom, 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 boom. You get to count them all. It could not be prettier than that. So we'll call that good. All right. Hopefully that was helpful. And off you go.